One of our roles is to run the Master of Technology in Intelligent Systems, where we focus on applications of artificial intelligence. Now, while it's true to say that artificial intelligence encompasses many more techniques other than deep learning, it's also true that probably one of the most exciting areas at the moment is deep neural networks and deep learning. Now, hence I've got great pleasure in introducing this morning Bhav, who's an expert in deep learning. He'll be telling us about the frontiers of deep learning. But before doing that, I would like to say a few words about Bhav's background. Bhav began his career with a degree in computer science and mathematics at the University of Texas in Austin. He then moved on to do a master's degree in computer vision at the Robotics Institute in Carnegie Mellon University. Then he moved to Niantic to become a computer vision lead. Now, if you remember, Niantic is the company that's well known for developing the Pokemon Go augmented reality game. And at Niantic, he was developing several state-of-the-art mapping and localization algorithms for augmented reality. He then moved on to Google Research, where he's a computer vision researcher working on large-scale object detection. And lastly, he's the founder of Neuron Labs, a startup company building software infrastructure for safer and more robust real-world deep learning. So enough of the introduction. I will now pass over to Bhav.
Hello, everyone. Thanks, Barry, for the introduction. And thank you, ISS, for hosting this talk as well. And also thank you to all the attendees who have managed to make it out here this morning. I'm really excited to present this talk, and I hope it'll be valuable to you as well. Without further ado, let me get into the talk. So this talk is going to be about the frontier of deep learning in 2020. And I'll also briefly cover the history of deep learning. And finally, at the end, I will introduce two pieces of new cutting-edge breakthroughs in deep learning that I'm excited to share. So the flow will be brief history, three trends that I see that are currently in place in the industry. And lastly, I'll end with two exciting pieces of research. Okay, so let's look at how it all began. So deep learning really got its start in 2012. Prior to 2012, people were mostly using classical ML techniques like feed-forward neural networks, multi-layer perceptrons, support vector machines, various other kinds of unsupervised clustering algorithms. And deep learning never really came to the front until 2012. So in 2012, AlexNet actually spawned the deep learning revolution by winning ImageNet. So ImageNet is a common image classification benchmark which contains over a million images of training data, and was kind of a benchmark to prove that deep learning actually works on real images and not just academic benchmarks. And so AlexNet won that competition in 2012, and this really spawned a lot of innovation in convolutional neural networks as well as large-scale deep learning. So you have VGG16 in 2014, ResNet 101 in 2015, which had 101 layers. And in 2016, we really saw the adoption of large-scale deep learning. So one of the main drivers for this breakthrough in the industry was actually the ability to train deep learning systems on GPUs. So Alex Krzyzewski, the founder of AlexNet, actually worked in the same team that I did at Google. And I heard this anecdote which said that he spent about 8 months trying to train the convolutional neural network that he created on 2 GPUs. And finally, he finished training it. And at the end, he got this neural network which beat the previous model, best model on ImageNet, by over 10% and achieved superhuman performance on ImageNet. So this was a really exciting time within Google as well as in the broader deep learning community. And this spawned a lot of innovation in CNNs. VGGNet, which was actually by a team in Oxford, won ImageNet in 2014, followed by ResNet in 2015, which was another step function over the previous model. If you look at the graph here on the right, you can see that in this period from 2012 to 2016, the size of the data actually remained constant. People were mostly using ImageNet as the benchmark. This contained about 1 million images. What changed here was actually the GPU power, which actually increased almost twofold during this period, which also allowed people to train larger and deeper models. And this really kind of brought brought deep learning to larger scale applications, as we will see here. So after 2016, we saw the expansion of deep learning to various other tasks and fields as opposed to just image classification. Everyone knows about AlphaGo, I presume, which is one of the popular mainstream kind of feats of deep learning. There's also further innovation in 2017 and 2018 on various other applications of deep learning. And finally, 2019 brought us exciting things like OpenAI 5, which is a Dota bot, which actually beat human players. And in 2019, we had realistic GANs, which basically allowed people to build hyper-realistic human faces and other objects, which were almost indistinguishable from real photos. So during this period, there were 3 main trends which drove a bunch of these changes. The first was the move to free data. Now it's kind of taken for granted that data is an important part of deep learning. But at that point, people were actually just discovering that we were able to scale with more data. The second thing was the move to learn everything. Instead of just optimizing the neural network, people started looking at the full stack of things to optimize. And the third trend was to use the existing data that you had and do more with it. So techniques like unsupervised and semi-supervised learning really drove a few applications like AlphaGo and OpenAI's Dota 5 bot. So those 2 things were actually pretty much dependent on unsupervised learning. And we also saw a bunch of other tasks using deep learning and kind of the growth of the deep learning industry. So if you look at the graph here, you can see that from 2014 to 2017, there were a few innovations in deep learning. But at 2017, we saw another jump from about 80 to 85% accuracy to higher than that. And this gain, although it seems incremental, actually offered a lot in terms of generalization of these models when you add more data. So we're currently at 2020, and there are a few things which I personally think are going to be the future. So deep learning has so far shown a lot of cool demos and worked well in controlled environments. But I think 2020 really marks the shift from controlled examples of deep learning to real-world deep learning. So we've seen, deep learning successful in the web, games, academic benchmarks, but certain applications like self-driving, GPT-3, and AR are starting to mature. And there's a lot of really cool research in 3D vision, few-shot learning, and domain adaptation, which I will share towards the end of this talk as well. Okay, so let's take a closer look at the first trend here. So I mentioned that data was valuable and that people wanted to get more data. And so people started exploring the move to free data. So how can we get data at a cheaper cost and get more data at the same time? So one of the main pieces of research that showed that data is useful is this paper here, Unreasonable Effectiveness of Data Revisited. What this shows here on the graph on the right is that the more data you have, the x-axis here shows the number of examples, the better your performance on your benchmark. So mean AP is kind of a proxy for the performance of your neural network. And you can see that as you add orders of magnitude of data more and more, your performance does indeed scale for the same model, right? So this is not a trivial fact here. The issue, though, is that labeling data is really expensive. It requires human annotators to label each image, and the cost of this can range anywhere from 50 cents to $10 US. So this is dependent on the task. So for an image classification task, you might pay about 50 cents per image. And for more complex, fine-grained tasks like semantic segmentation, it can cost as much as $10 per image. So if you just do the math and look at the order of magnitude of examples you need, which is about, say, millions of examples, this can easily cost millions of dollars to train a single model. And the other problem here is that a lot of the data that we actually use in the industry is generated by consumers. Either they provide the data or the data is mined on the web. And since 2016, with the introduction of GDPR and the implementation of GDPR in 2018, this has imposed a lot of restrictions on what kind of data you can use. And there has been a lot of a push to be more responsible with user data and make sure that you don't expose consumer PII to people who annotate the data and so forth. So there's really a kind of a push to get more data and maintain the quality of the data. So to this end, we've seen a few technological advances in research to enable this. So one of them is known as knowledge distillation, where instead of having humans label the data for you, you use machines to label the data for you. There's some trade-offs here, which we'll discuss, but this is very extensively used in the industry. The other kind of push for image data is to use 3D supervision and project that back to 2D. So the idea here would be to reconstruct your scene in 3D, label it, and then profit by getting free annotations in 2D. The last kind of trend here, which is starting to get more common and get more adoption, is the use of synthetic data. So here you're not just labeling data, but you're generating the data itself. And the labels are acquired automatically through that process. So knowledge distillation, like I mentioned, is using a machine to annotate the data for you. So what this is use a pre-trained teacher model, which is trained on some small amount of data. You present a large amount of unlabeled data to this teacher model, and the teacher model produces a label. So now you have an image and label pair, and you can use this to train your student model on the newly annotated data. So of course, this doesn't come for free. There's no free lunch. Machines aren't always accurate and can produce errors. And especially if you've already trained a teacher model on some small data set, there's a tendency to carry over the bias learned from that data set. So I won't go into exactly what the advances are to fix these problems, but I'll list them here. They are self-distillation, multi-teacher distillation, and even using human in the loop to correct some of these noisy predictions from your teacher model. And all of this has really increased the order of magnitude of data available for deep learning today. The next thing is 3D to 2D supervision. So as I mentioned, this is for image data. Right? So the idea here is to reconstruct a scene in 3D using some kind of a video sequence or so. This is pretty much very commonly done today if you have any kind of video data like YouTube videos or so on. And then your annotation is actually done in 3D. So I'll actually show an example of what this looks like. So here you can see a 3D mesh reconstructed from a video sequence or any other kind of video data. And human annotators actually annotate the 3D objects. It's pretty difficult to do, but you only have to do it once. And once you have a fully annotated scene, you can actually get rendered annotations like the ones you can see in the bottom row, where you have the real image on the left, and you have the depth map in the center, and you have segmentation outputs on the right. So you can basically render this scene from many different viewpoints and get free supervision that way. The last kind of trend here is to use synthetic data. So instead of reconstructing a scene, you can think of just generating the scene using synthetic models. And this way you can get many different variations of the scene. So you can basically arrange the scene any way that's useful for your task and also get the supervision. So this does require some human input, and the rendered images may not be as ideal as the real captured images for your application. And this is how it looks. So you have a 3D scene here, which is basically a house. The top left shows the rendered image, and you can see it's not exactly like a real image, but it's still useful because it contains these objects and represents the geometry of the scene. The right shows the top right shows the rendered segmentation outputs, which is basically much better than a human could annotate, and you can render it from many different viewpoints. You also get things like the depth map, which is notoriously difficult for a human to label. And you also have a map, which you can use to automate your rendering. So this is actually, this slide is from Unity, who is a kind of a 3D engine company. And this shows you the power of synthetic data. On the left here, you have the column about synthetic data. You can generate a data set of, say, 1 million examples or so for about $7,200, whereas it takes about $4,800 to label 1,500 real-world images. So the order of magnitude in terms of the cost is over 1,000-fold here. And synthetic data, while difficult to use, is a very strong source of data. And if you can figure out how to use it well, and for certain applications, certainly it has been used well, you can really benefit a lot from this. And so a second trend here is to learn everything. So instead of just optimizing your neural network for a specific task, it turns out that you can actually optimize the full stack. So on the right here, you can see the classical paradigm of deep learning, which is you get some labeled data, you perform data augmentation on this data, you feed it to the model, and you optimize the model based on the loss function. However, there are many things you can optimize here, including architectures, optimizers, even the data augmentation step can be optimized. And you can also optimize learning schedules and so on. This whole field is called AutoML, or learning to learn. So for the purposes of this talk, I'm just going to focus on the most exciting thing here, which is the architectures. People typically design these architectures by hand because they believe that human intuition was an essential component of this. Most of the early architectures were from pattern recognition or electrical engineering. The kind of concept of convolution is from electrical engineering, and various things like pooling and normalization were all from pattern recognition. So people were kind of stuck in that paradigm until about 2018, where the first paper which did neural architecture search was released. And this really spawned like the application of various techniques such as reinforcement learning, supervised learning, evolutionary algorithms, and so on, to discover new architectures based on some data source in a data-driven manner. So this paper here, which I'll briefly discuss, used over 800 GPUs, and people have since come up with ways to make this process more efficient. But this process is really very resource consumptive. But the promise here is that if you can discover one new architecture, you can actually amortize the cost of this over many different applications. So as I mentioned, neural architecture search was a paper released in ICLR 2018. And the idea here was to use reinforcement learning to sample an architecture from a different model called a controller. So the controller would actually generate an architecture from scratch. And this architecture would be trained using your standard deep learning training process. And your accuracy of this trained model would then be used in reinforcement learning to train your controller to generate a better model. So this process was done iteratively over about a few thousand epochs. And finally, they were able to generate an architecture which looked something like the one here on the right, which is fairly complex and something that a human would probably not be able to make sense of as the best architecture. But still, at the time that this was released, it was the state of the art, and it really blew away the field at that time and spawned a lot of new research directions in automating several parts of the deep learning stack. So the third thing here, do more with less. So we spoke about how to get more data, but you can only do that up to a finite point. At some point, you have a large data set, and you really want to do more with whatever data you have. And there may be cases where getting a larger data set is even difficult. So you really want to make sure you can do more with less. So for this specific thing, there were three main drivers. Of course, there are a lot of papers in this field of semi-supervised and unsupervised learning, but these three techniques really showed state-of-the-art results in this. So first is self-training, which is using unlabeled data to learn more from it. Self-play, which is to use AIs to compete against each other to produce the best model iteratively. And self-attention, which is to learn associations within your input data. Okay, so self-training is a pretty simple concept. What this is basically to use a single model and use the outputs of this model with noise injected in it to iteratively improve the model. So there was a paper released in 2019 called Self-Training with Noisy Student, which was a state-of-the-art, which is the current state-of-the-art on ImageNet, which uses this technique. So what it basically does is in the first step on the bottom left here, you can see that it labels an example using the current model, which you've trained on a small amount of labeled data. So here you get a label of cat for this image. And then you add noise to this image and you train with the label that you've acquired previously. You do this iteratively and you expand the model and you can improve the performance of your model for basically free this way. And this is, like I mentioned, current state of the art and is used in many different applications other than ImageNet. The second, in my opinion, the most exciting way that we do more with less is to use self-play. So in self-play, AIs use reinforcement learning to pit themselves against one another and iteratively improve your model over time. So on the bottom left, you can see OpenAI 5 self-play in Dota. So you actually have different Dota teams, which are both AI, competing against each other, and whoever wins at the end will be the new champion, which will then be replicated and trained again. On the right here, you can actually see an instance of a Go game, which is match 41 of the self-play procedure with AlphaGo against AlphaGo. And self-training here for Go was actually one of the key breakthroughs in discovering newer creative moves in Go. So the search space of Go is huge, and if you are solely influenced by human games, it's going to be difficult to have any kind of creativity or surprising moves. But people saw that using self-play here actually allowed AlphaGo to discover creative moves which humans may not necessarily be able to come up with. And the last thing in this section is self-attention. So self-attention was introduced. Self-attention actually existed quite a while in the field of deep learning in research. However, it was really kind of one of the breakthrough moments in this paper called Attention is All You Need, where it was used with transformers. So transformers are the current state of the art in multiple language tasks, and is even the basis of one of the cutting edge research breakthroughs, which is GPT-3, which is generative pre-training 3, which we'll see shortly. And the way attention works is as follows. Here's an easy example. So consider the sentence here, which says, the animal didn't cross the street because it was too tired. What does the word it here refer to? Does it refer to the animal or the street? For humans, it's pretty obvious that it refers to the animal because streets can't get tired, right? But for a language model which just views this whole sentence as nouns, verbs, and so on, it does not really know which one to associate the word it with. If it looks at the sentence on a token by token basis. Self-attention, on the other hand, allows the model to look at the entire sentence and form associations through training on various language understanding tasks. So GPT-3 here is able to look at it and clearly say that the probability of it being associated with animal is higher. And this figure on the right shows you what the architecture looks like. It's not too complicated. It just has a few steps, but it's surprisingly powerful. Okay, so that was the current trends that I see in deep learning. And now I'm going to shift over to the future of deep learning, which in my opinion will be characterized by the expansion of deep learning into the real world. So in my mind, there's two properties of the real world. The real world is really complex. It's much more complex than these controlled environments like academic benchmarks or even games like AlphaGo, which is basically several orders of magnitude more complex than the amount of atoms present in the universe, right? And I think the real world is even more complex than that. There are many things that can happen at any point in time, and it's sort of unpredictable. And the real world's also fundamentally in 3D. So we do need to have a good understanding of 3D if we were to deploy applications such as self-driving car or augmented reality in the real world. And there are two key pieces of research here which are needed to drive these applications in the real world. One of them is domain adaptation and few-shot learning. So you want to be able to adapt to these changing environments instead of being brittle and only focus on very small domains of application. You also need to understand the scene, 3D scene pretty well if you want to operate in the real world. And so I think 3D scene understanding is quite pivotal here. So to this end, there's actually two core pieces of research which are breakthroughs and have shocked people, even experts in deep learning. And they've all come about early this year in 2020. The first one is called Generative Pre-Training 3, GPT-3. A lot of people might have seen examples of this in social media, and it is really very exciting, even as someone who has seen a lot of deep learning models. It's able to adapt to the environment using few-shot learning, which is one of the key insights that the authors of the paper describe in the paper. And it generalizes pretty well, as we will see shortly. And a kind of less known but very recent breakthrough in the field is also known as neural radiance fields, NeRFs. This is more geared towards 3D applications and computer vision, and has really surprising qualitative results, which are much better than any 3D reconstruction or scene understanding method that we've seen in the past. So a brief overview of GPT-3 is that it's based on the transformer model, as I mentioned. It uses generative pre-training to train the model on over 1 trillion words, which are scraped from the web. And it adapts to the environment by the user specifying a few examples of what they want to adapt this to their task. It is very large scale, so OpenAI in conjunction with Microsoft spent over $12 million to train this single model. And this model contains over 175 billion parameters, which is 10x more than any previous model. So we will briefly describe what the applications of GPT-3 are here. So here you can see that you have a kind of a prompt here, a console, where people can specify queries in natural language, like what day is it? And GPT-3 takes that and maps it to a command line command here, which basically gives you the date and the day, and also allows you to make corrections based on the context of what you've typed. You can also specify things like, clone this repository and install it. automatically figures out where the repository is and clones it. It's pretty exciting. In the future, software engineers can probably use this to transform their ideas and into code. I don't think it's going to replace software engineers because you still need someone to write the prompts in natural language, but I think it really saves a lot of time. You can also use it to design UI. So here you see a text box where a designer would type a description of what they would like to design. And the designer can specify they want a camera icon, navigation bar, and so on. And when they click design, GPT-3 automatically comes up with the UI and presents exactly what the user wants. And this, although it's a demo, it's actually a release as a prototype. So you can try it out yourself to see whether it works. And people have generally got it to work on whatever they want to do. So it's really surprising that this works. You can also use GPT-3 to learn from people. So in this case, you can specify a teacher here, let's say Elon Musk, and based on whatever information is available in the web that the model has learned, you can actually get a realistic answer to your question. So here the prompt is teach me about rockets. And the result is that rockets can be used for launching objects into space and so on, propelled by rocket fuel. This answer actually makes a lot of sense. There's a lot of examples on social media which are kind of funny and don't make sense. So it can go wrong at times, but it's surprising that the model is even able to come up with such a coherent and cogent response to a fairly complex question, which humans may not even be able to respond comprehensively. So there are other applications, such as writing stories, psychotherapy, food recipes, and so on. Someone actually made a recipe from GPT-3 and presented it as pretty fun. Also medical diagnosis, which raises a lot of questions about the ethics of this, and composing music, which shows that you can use it for creativity and so on. Okay, the last piece of research here, which is personally very exciting to me, is the introduction of neural radiance fields, also known as NeRF. So what this does is it takes a sequence of images and reconstructs viewpoints from these, which these images were taken from. And these viewpoints are reconstructed using traditional pose estimation techniques. So basically, you just need a set of images as the input. And your result from this is a 3D reconstruction and view-dependent rendering. So you can see this a graph of the inputs and outputs on the right here on the bottom right. You basically input the viewing angle and position, and you predict the RGB pixels and the density. So I'll present an example to show exactly what this looks like, but it basically learns a mapping from rays through images to RGB values, as you can see on the bottom left. I think this is best described through images. So this is what it looks like. NeRF can produce pretty photorealistic rendering that accounts for lighting, materials, and viewpoints, which previous reconstruction techniques are not very good at. So on the left here, you can see what an example of a classical reconstruction and rendering would look like. It's not exactly photorealistic and contains many gaps and so on. And it does not really capture a lot of the view-dependent characteristics that NeRF captures on the right here. So you can see that it's a scene here in the conference room. You can see that the lighting and the reflections on the television are pretty well captured, and that the whole thing is almost indistinguishable from a real video. Right? It's very photorealistic. Here you can see a scene with a lot of specularities and shiny objects here. You can actually just fix the viewpoint and vary the viewing angle to really show how NeRF is learning these two things separately. So here on the right, you see that the viewing position is fixed, but if you vary the angle, you can actually see some of these view-dependent effects. NeRF is also really, really good at learning these fine physical structures here. You can extract a depth map from NeRF, which is here on the right, And you can see that the various petals and leaves of this flower are actually learned just based on a set of images. So this is actually quite exciting stuff. One of the useful things about NeRF is that you actually can apply this to the real world. So it's not just in very controlled settings that this works. Here you can see on the left a reconstruction of the Trevi fountain based on user submitted images. It's quite detailed, very accurate, and you can render it from many different viewpoints. And this work was just released about less than a week ago, so it's pretty much cutting edge research. And on the right here, you can see the same is done for the Brandenburg Gate. It is quite impressive that it learns all the fine structures. And the good thing about learning this neural representation as opposed to an explicit 3D representation of the scene is that you can use various kinds of interpolation in the feature space of this 3D model, of this neural model, to vary some of the quantities like lighting, or even use it for other tasks like multitask learning. So this sequence here shows you that you can basically specify a input to the model, which is time of day or lighting. And the model learns these correlations and is able to relight the scene based on any viewpoint. So it starts off in the morning, and slowly as the interpolation progresses, you can see how it changes to the nighttime. And you can see, if you notice here, it even captures that there's certain lights below the statues that are switched on towards the evening. And this is very useful in any applications that you want to use for a real world, because it captures various separate conditions that you would see in the real world. So yes, this is a pretty new research just released a week ago. With that, I conclude my presentation, and I invite Barry to ask questions that the audience members have submitted. Thank you.
Okay, thank you, Bav, for that fascinating talk. There's plenty of questions coming in. Here's one question. For the algorithm that finds best model architecture, will it take a lot of computational resources such that it can only run on a cloud?
That is a really good question. And this is something which researchers are actively trying to answer. So since the paper in 2018 of neural architecture search, there have been a lot of advances which have tried to make this architecture search process more efficient. So some papers claim that you can just use a single GPU to discover this architecture. The good thing about this is this architecture search process needs to only be done once. So once you do this process, you can reuse that same model across many different tasks and use it iteratively. This best model can also be a smaller model. So you can specify a constraint into the architecture search process to actually get a compressed model. So you can envision this working on an embedded device or a mobile phone or so on. So although it does take a lot of computational resources at the start, the result would be a model which can run efficiently.
Okay, well, I would like to ask a question also relating to the architecture search. If we have auto ML generating architectures for us, and potentially very complex architectures, then does this not make the black box problem even harder? We will have architectures that we have no idea what's going on inside. Do you see that being an issue?
Definitely. So it is true that current neural networks are really difficult to understand and explain. But I think the nature of this problem stems from the optimization process, where you learn weights and for these convolutions, which somehow, when assembled in a sequence, produce a result which humans can understand, but the intermediate layers are not explainable. I don't think that this architecture search process exacerbates this problem, since it's isolated to each layer. But I do think that it does not improve it in any way. It does indeed still pose that issue. And there actually have been some techniques to use neural architecture search to determine what the network is actually learning. So things like auto-augment, which try to augment the data, give you some insight as to what kinds of data actually help this neural network solve this task. So I think it can be used in a way to improve explainability as well.
Here's another question to do with the computing power required for deep learning. You may have just mentioned some of this in your earlier answer. Does deep learning rely on silo computing, supercomputing power? And is deep learning going to make use of 5G, or are they independent?
Okay, these are two good questions. I'm not sure exactly what silo supercomputing power refers to, but I can talk about the efficiency of deep learning as I've seen it. So within Google, we do have a large cluster of machines which are used for deep learning. And indeed, large-scale deep learning does rely on this kind of cluster of supercomputers today. The main kind of use of this compute stems from the fact that there is a very expensive optimization you have to do iteratively over a lot of data. But there are a few techniques to reduce this compute by using transfer learning, where for each new task, you don't re-optimize the neural network, but you just use a previously trained model and update it. So today, I would say it does rely on heavy compute, but in the future, we might see more efficient optimization processes for specific applications. For the second question of 5G, I think as of today, they are quite independent, but I do see 5G being very useful in training neural networks on the edge. So there's this concept of federated learning, which basically allows you to optimize your neural network on the edge as opposed to doing training on the cloud. And for this use case, I think 5G is going to be essential in transferring back some of the gradients after you've learned to optimize on your specific use case back to the cloud. So I'm quite optimistic about training deep networks on the edge using 5G.
Okay, good. Here's one asking whether the NeRF model was used for Facebook 3D photos.
Facebook 3D photos. So I am not 100% sure if they're using that internally, since I don't work at Facebook. But there have been similar technologies to NeRF that have been able to reconstruct a 3D scene like what NeRF looks like. The key difference is that NeRF does this completely in a single neural network, as opposed to using classical geometry approaches. And I think that is one of the key differentiators between existing methods and NeRF.
Okay, good. Here's one. How might NeRF change the media and gaming industry? And I guess I'd like to tag on to this about GPT-3 and how that's going to generate the media and the news industry with fake news, etc.
Definitely. In fact, we're already seeing that. I read a blog post where the author argues that GPT-3 is not a threat to social media. And at the end of the blog post, he reveals that that blog post was entirely generated by GPT-3. And it was very shocking. And indeed, GPT-3 is going to be a huge kind of generator of fake news, or in fact, even news which is accurate, because GPT-3 has the potential to generate really accurate facts and even like insights and inferences. So it might even help in some sense. But yeah, I think the solution to that is to actually develop more techniques to identify things generated by neural networks, as opposed to have regulations stop it, because that's pretty much impossible. In terms of NeRF, I think it can be used to generate high quality assets, real world assets, especially in AR, where the user holds the phone in their own hands. NeRF can help you generate a 3D reconstruction of whatever object you have at your own home. It might be even something special to you, like your favorite cup or your favorite pet, or so on and so forth. So there's a lot of model customization opportunities with NeRF.
Good. Here's one we can look at. Can you share some advances in the field of federated learning, opportunities and research directions?
Sure. The advances in federated learning are pretty much mostly held internally within companies like Google and Facebook. So there's not a lot of external like research papers released about federated learning. One thing I can share here is that the advances are moving pretty rapidly, and people are using these domain adaptation techniques in conjunction with federated learning. So it's something that's really powerful and on an application basis, and maybe not so exciting on a research basis, but they're just trying to find ways to expand the use of federated learning.
Okay, here's one I'm sure that a lot of people are going to be interested in. I mean, we know that the language Python is obviously very well known for being associated with deep learning, but are there other programming languages very relevant to deep learning?
At this point, I would say Python still is the kind of king of programming languages for deep learning, precisely because there are a lot of frameworks which work really well in Python, like PyTorch, which is built specifically for Python. C++ is used a lot in the industry with things like TensorFlow, but for prototyping and research, I think the most relevant language is still Python.
Very good. Here's another one. What are the good resources that are available to learn more on deep learning?
Sure. So Google has a good introduction to machine learning and deep learning in general. I would recommend Andrew Ng's course on machine learning. That really gives a lot of motivation and background into why we use deep learning. And Fast AI also has a really good course, which is more hands-on, and I highly recommend that as well.
And I guess relevant to that question would be to ask you about where you see the job opportunities in deep learning. How big is the opportunity outside of the research world?
I think it's huge, and ISS probably has a lot of investment into this, so they probably have a good perspective. But I think as things are moving more remote, there are a lot more opportunities in deep learning, especially since a lot of deep learning jobs are dependent on the scale of compute and data that you can acquire. So those opportunities are now, open to everyone. And I think that things like GPT-3 actually create more jobs because you need a lot of data science expertise in order to train these models and customize them really well.
Okay, that's great. I guess I've got time to squeeze in one last question, put you on the spot here. You said that in this year, 2020, you see perhaps potentially a big shift. Using a crystal ball, what do you see the next big breakthrough might be in deep learning?
That's a great question. I can speculate a little bit, and I would say that the field of 3D understanding is moving really fast. So NeRF is just the tip of the iceberg there, and I think we'll see a lot of different fields of research within 3D expanding, like things like monocular depth, which is basically getting a 3D representation from a single image. I think also moving images are notoriously difficult to reconstruct. So video is really difficult to reconstruct if they're moving objects. And I think there are going to be a lot of breakthroughs from deep learning on that front.
Okay, Bob, I think we're going to have to break there. We've run out of time. So I'm sure everybody would join me in thanking you for this great and very interesting talk. And I'd also like to thank the audience also for joining in and listening to Bob this morning. With that, I would like to end this session and say goodbye and good morning to you all.